Welcome. As we get ready for our upcoming test in Chapter 10, I wanted to walk you through the area of a regular hexagon. You remember that in 10.4b, we constructed, first of all, a square inside of a circle, and then we constructed a hexagon inside of a circle. And then real quick at the end of the class there, we found out we calculated the area of a regular hexagon. We did it first of all with a side length of 6 units, and then we also did it with a side length of 3 units. And I went very quickly through that. There will be a question on the test that is similar to this, and so I wanted to slow down and make sure that you got a clear description of how to do this. We have done areas of regular polygons. You will remember back in 11.3 were the notes, and I would recommend, as I handed out in class to you, this half sheet of paper, the area of a regular polygon, this procedure here. And so I will essentially be following that procedure when I go through this. Now, you do not have this sheet of paper. I just made this so I could lay things out nice and clear for us. So here's our hexagon. It has 6 sides to it, and you remember that we create this right triangle in it. And this is the radius going from the center to a vertex, and this is the apothem going from the center to the midpoint of a side. So if S is, let's call the length of a side S, and then X here is half of that length. You remember that the equation for the area of a regular polygon is 1/2 the apothem times perimeter. Sometimes you'll see that switched. I think in some of my posters I have 1/2 perimeter times apothem, but you know it does not matter what the order is. Our first calculation that we can always do, is find the central angle. The central angle. You remember the central angle is this entire angle going from radius to consecutive radius, this entire one. And there are as many central angles as there are sides in the regular polygon. And so we take 360 degrees, divide it by the number of sides. In this case we are using a hexagon, so 360 divided by 6 gives us 60 degrees. And then we find our top angle here. So that's half of the central angle. 60 degrees divided by 2 gives us 30 degrees. Now we are ready to take this right triangle here and kind of blow it up and write it over here on the side. And we can make designate our numbers more easily. So we know that this top angle is 30 degrees, and we also know that the apothem comes down against the side perpendicular to it. So this is 90 degrees. And now you're thinking, hey, wait a second, if this is 30 and it's also a right triangle, then I know the other angle has to be 60, because the sum of the interior angles of any triangle is 180 degrees. So this dude is a 30, 60, 90 triangle, a special right triangle. So you could use trigonometry if you wanted to in order to find the apothem. Remember, we are trying to find the area, and so we need the apothem and the perimeter. So to find the area, the apothem, we could use the tangent of 30 equals the opposite, which in this case is 3, over the adjacent, which is the apothem. But it's easier to be able to use, I think it's easier, to be able to use the special right triangle of a 30, 60, 90 triangle. And you will remember that when you see 30, 60, 90, you should think of 1, 2, and square root of 3. So here's our pattern, and we will put that in the same orientation as this problem that we're trying to solve. And you remember that 2 is longer, is a bigger number than square root of 3, which is approximately 1.7. And by the way, this is all coming from 7.4. So if you wanted to review how to do special right triangles, you can go to your 7.4 notes, and here's the 30, 60, 90 triangle, and that pattern of 1, 2, square root of 3. So square root of 3 is approximately 1.7, which is smaller than 2. So 2 is going to be on our hypotenuse, which it is here. Here is 2. And then remember that the smallest side, that is 1, is across from the smallest angle. So it's across from the 30-degree angle there. So now we have our pattern set up alongside of our problem. And where did I get this 3 from? Well, remember I said, as you know, if we have a side length of 6, this x here is going to be half of that, because this is the midpoint of the side. So s divided by 2 is 6 divided by 2, which is 3. So the length of this bottom leg here is 3. So remember, similar figures means same shape and proportional sizes. So let's create a proportion between these two similar triangles. And so a over square root of 3, those two sides correspond to each other. A over square root of 3 equals 3 over 1. So here's our proportion. In order to solve this, yes, it is true that you could cross multiply, but I think it's easier to get rid of the denominator by multiplying both sides by that denominator. So multiply both sides by square root of 3, and the square root of 3 cancels out here, and my apothem equals 3 square root of 3. So we now have the apothem. All we need is the perimeter to be able to find the area of this regular polygon. So the perimeter, as you remember, just add up the number of sides around this regular polygon, and another way of doing it is multiply the number of sides times the length of each side. So there are 6 sides, and each of the sides we were saying is 6 units long. So 6 times 6 gives us 36. So now we take those two numbers, plug them into our equation, and our simplified radical form. Yes, it is true that you could find a decimal, but you'd have to round that thing off. It's better to leave this perfect number of 54 square root of 3. 1/2 times 36 is 18. 18 times 3 is 54. So the area of a regular hexagon whose side length is 6 will be 54 square root of 3. Let's also do this as we did with if the side length was 3. So we do it very similar. Of course, the central angle and the top angle, that does not change. So we can create the same pattern here, or the pattern to the right, but also the problem is all the same except for our side length is 3. Therefore, the x, this bottom leg, is going to be 1.5, half of 3. And when we do our proportion, we find out that the apothem on this guy is 1.5 times the square root of 3. And then for our perimeter, since we still have 6 sides, but the side length is 3 instead of 6 before, so 6 times 3 gives us 18. And so now plug those two numbers into our equation for formula for the area of a regular polygon, and we come up with the area of this smaller polygon, or hexagon, with a side length of 3 is 13.5 times the square root of 3. Now, if they were to ask you the difference in area, all you would do is just subtract these two differences. And it might be a little bit strange for you to say, okay, I have 54 square root of 3 minus 13.5 square root of 3. I'm just taking those down. But treat this like a variable. If you had 54x minus 13.5x, well, that's simple enough. You just say 54 minus 13.5, and then you'd have, just keep the x there, right? Same idea with the square root of 3. Okay, just subtract those two, and you get 40.5 square root of 3. That's the difference between those two areas. Or they could ask you for the ratio of change, and this one we did do in class. So if you had the larger one up on top, 54 square root of 3, and the smaller one underneath that, of course these square root of 3s would cancel out. And so 54 divided by 13.5, according to my calculator, is 4. So what does that tell us? It tells us that when we multiply the side length by 2, we went from 3 up to 6, then the area becomes multiplied by 4. So you double the side length, and it results in quadrupling the area. And why is that? Because the side length shows up both in the apothem. See how our apothem is double the amount, and it also shows up in the perimeter, the calculation of the perimeter. Our perimeter is double, so they have double 2's. Either way you say it, 2 times 2, which is 4. So if you double the side length, you end up with quadruple the area. Okay, so make sure that you're able to do that on your own. And again, I would recommend using special right triangles. I think it's the easiest way to do that. All right, hope that's helpful, and I look forward to seeing you soon, and may the Lord bless you.